objectives for this section are to understand the set of real numbers, the subset of real numbers, which we'll go over in a moment, order numbers on the real number line, determine distance and absolute value of numbers in one dimension, or in other words, on a number line. So let's talk first about the real number system and the different subsets of the real numbers that we like to refer to as time goes on. Now I'm going to give you the notation. In your book you'll notice that a capital double-stemmed, I call it a double-stemmed N here. It's because we don't draw a bold-faced N when we draw it on the board or on paper, but in the book it's going to look like a bold-faced N, and you'll know that means a set of natural numbers. So the set of natural numbers we can actually list. Each set for anything is enclosed by these curly brackets. So you'll know that now we're talking about a set as soon as I write the curly brackets down. So the set of natural numbers starts with the number 1. It's basically the set of counting numbers, and it goes on forever. So there are infinitely many numbers in the set of natural numbers. And the ... there is really important because it tells you specifically that I've established the pattern and that pattern continues forever. The next set of numbers is the set of whole numbers. In your book it will be denoted by a bold-faced capital W, but in writing we just write a double-stemmed capital W. The whole numbers is a set that contains the natural numbers, but it also adds to that set the number 0, which is actually a really important number. And if you ask little kids about 0, they don't really understand it. It's quite an interesting concept, the whole concept of 0. Try it out. Ask a 3-year-old if he wants 0 cookies. Well, you better have a cookie, because a 3-year-old will get upset if you say no. But 0 cookies, you and I know, isn't really no cookies, but a 3-year-old doesn't really understand that yet because it's an interesting concept for someone to grasp. Okay, I could say a lot more about 0, but let's go on to the set of integers. This is denoted by a capital double-stemmed Z or bold-faced Z in your book. We can still use list notation for this set, but notice that it goes off to infinity in either direction, going off to positive or negative infinity. Well, whatever that means, because of course positive and negative infinity are just ideas, they're not numbers. But you see the ... needs to be going on each side. So the set of integers is all the whole numbers as well as their negative counterparts. And the set of rational numbers now, okay, I guess I'm writing a little too big. The set of rational numbers is double-stemmed capital Q. Q for quotient. So rational, if you see that word, it contains the word ratio, and anytime you see the word ratio in mathematics, it means something about a fraction. Or Q for quotient. And for the rational numbers, we're not going to be able to list them in list. We're going to have to use set builder notation. So let me explain this as I'm going along. I'm going to say the rational numbers is the set containing all fractions a over b. So this means, let's do this. This means such that, in set builder notation. Okay, so it's all the fractions a over b such that a and b are elements of the integers with the one exception that b cannot be 0. So this symbol here means element of. So now you know a little bit about the notation. And I'll expect you to know the notation as time goes on and as we're getting through this class, because it's nice notation and it simplifies writing things down mathematically. So the set of rational numbers, again, is a set containing all fractions such that the numerator and denominator are integers, but the denominator can't be 0 because we can't divide by 0. The numerator and denominator being integers just means it comes from, it's one of those numbers from that set of integers. So let me just do an example quickly here. If I look at the number 5, since I can write 5 as 5 over 1, it would be considered a rational number because I can write it as a fraction with integer top and bottom, or I could write it like this, 10 over 2 or something like that. There are lots of different ways I could write 5, but that would be considered a rational number. Okay, the set of irrational numbers, that's kind of a trickier one. So notice that the prefix ir means not. So irrational literally means not rational. So it's all the numbers that are not rational. We don't have a good symbol for irrational numbers. We can make one up, but it wouldn't really be standard. The set of irrational numbers, So this is usually how we write it. This isn't going to make sense for a moment until I define what that double-stemmed capital R is. The set of irrational numbers is all the real numbers without the rational numbers. I'll give you some examples in a moment, but let's talk about real numbers. Real numbers is everything on the number line. Let me just write that in words. Any number you can think of, basically. So the set of irrational numbers, oh, and here's another little note about notation. The squiggly equal sign just means approximately equal to, which is very different than the regular equal sign. Okay, so another example about irrational number. Oops. So let's look at, probably pi is the most common example of irrational number that most people know. So the reason it's an irrational number, or one way I can tell that it's an irrational number, is in decimal form it never repeats and never ends. Another example of an irrational number would be square root of 2, square root of 5, cube root of 6, something like this. So anything that you can't really simplify with, if it's a square root, for instance, it's a square root of a non-perfect square. Let me just say in decimal form, this is probably going to be the easier way to tell the difference between a rational and irrational number. In decimal form, we've got three different kinds of decimals. So we have terminating decimals. That means they end. So here's an example. So terminating means literally it ends. So an example would be 0.75. So that is a terminating decimal because it ends and it doesn't keep going, basically. There's two different kinds of non-terminating decimals. Non-terminating and repeating, or I'm sure you can guess this one, non-terminating and non-repeating. So let me give an example of each of these. A non-terminating but repeating, if I could write EX for example, is 0.3 repeating. So there are a couple ways we can notate this. I can either write 0.33333 with the dot, dot, dot indicating it goes forever, or I can put the little horizontal line segment above 3 so it indicates it goes on forever. So this doesn't end. As you can see, it goes on forever, so it's non-terminating, but it does repeat. The 3's keep repeating. And then there's this example of a non-terminating, non-repeating. So let me give you an example here that's a good one because it tests your skills of whether this is really repeating. So notice that the dot, dot, dot is indicating it goes on forever, so it's non-terminating. It's non-repeating even though this is patternistic, right? You can predict what's coming next, but it's not repeating because it's not repeating the exact same thing over and over again. So let's classify these different kinds of decimals. So in decimal form, a terminating decimal is a rational number. A non-terminating repeating decimal is also a rational number. So what this means is both of these types 1 and 2 can be rewritten as a fraction. In other words, let's look at 0.75, the example I gave you. This can be written as 3/4, and 0.3 repeating, perhaps you know, can be written as 1/3. So types 1 and 2 of decimals can be rewritten as fractions with integer top and bottom. Oops, I don't know what I was about to write there. Okay, so type 3 here in decimal form, this is the only kind that's an irrational number. So a non-terminating, non-repeating. If we go back to our example of pi, you'll see, you can Google this, pi, if you go out, it has 3.14. Who knows? A lot of people know a lot more digits than I do, but the point about pi is that it never ends, the decimal never ends, and it never repeats. Okay, let's go on to the next slide. So let's do this example 1. To which sets do each of these numbers belong? Well, we've already talked about pi. That's a little bit of a giveaway. Now, when I'm asking about which set they belong to, I'm asking about the smallest set to which they belong. So for instance, a rational number could also be an integer, a whole number, and natural number. So let's think about 3/5. We'll look through the number sets. Is it a natural number? 1, 2, 3? No. Is it a whole number that includes also 0? No. It's not an integer, but it is a rational number. So I'm going to say this. This one goes in D for rational number. Negative 2 is not a natural number because it's not one of the counting numbers. It's not a whole number because it's not a counting number or 0. But it is an integer because it's the negative counterpart of a whole number. Cube root of 8, okay, this is a good one. Cube root of 8 is asking what cubed gives me 8. And in fact, this reduces itself to be 2. So you can't just look at things on the surface level. You have to actually simplify it and then decide what's going on. 2 happens to be a natural number. And do you notice also that it's a whole number, it's an integer, it's a rational number. But we're asking for the smallest set to which it belongs. Okay, pi, we already talked about. This is an irrational number. Square root of 2, if you remember my previous example, the square root of 2, because 2 is not a perfect square, it cannot be reduced. And in decimal form, this is going to be a decimal that continues on forever with no repeating. Please notice that when you plug in square root of 2 on your calculator, it will end. That doesn't mean it's a terminating decimal. It just means your calculator only has so much space. Okay, 0. That's probably one of the best questions we can ask you. Is it a natural number? No, it's not one of the counting numbers. The smallest set to which 0 belongs is B for the whole numbers. And 7/3. Okay, that can't really be reduced. So it's not a natural number, whole number, or integer, but it is a fraction with integer top and bottom, so it's a rational number. Example 2 says, put each of the numbers above on this number line. Okay, so basically we're just trying to make sure that we understand how things are ordered on the number line. Okay, so let's draw everything in red then. 3/5 is a little bit bigger than half, but less than 1. So I'm going to put that about right here. 3/5. Negative 2, right here. It's cube root of 8, which we said reduced itself to 2, goes right here. Pi is somewhere 3.14, so that's a little bit bigger than 3, so about right there. We can't be exact. Square root of 2 is something like 1.4, somewhere around there. So it's a little bit less than 1.5. 0, okay? Here's 0. And 7/3. So 7/3 is a little bit bigger than 2. It's 1/3 bigger than 2. So that's about right there. So there are all the numbers plotted on the number line. So if I wanted, I could also write an inequality statement about this. So A less than B. So we read this as A is less than B. And the other one, of course, we would read as A is greater than B. Keep in mind that you can read these going from left to right or right to left. So we could also say equivalently that B is less than A for this last one. This is the same as B is less than A. So if we order these numbers that we had on the number line here, the ones in red from the previous example, we would have negative 2 is less than 0, which is less than 3/5, which is less than square root of 2, which is less than cube root of 8, which is less than 7/3, and finally less than pi. So we can write that compound inequality there. Compound, when I say compound inequality, I just mean that it's more than one inequality sandwiched together, basically. All those things are true. The distance between 2 points. So if I ask you the distance, let's say it this way. The distance between negative 2 and 5 is what? Keep in mind, right now we're talking about distance in 1D. So let me write that up here. 1D meaning one-dimensional. So number line is just one-dimensional. A plane or the surface of a paper or board would be two-dimensional, and most people agree we live in three-dimensional space. So the distance, we're going to give you different distance formulas as time goes on. Distance between 2 points in 1D, distance between 2 points in 2D, 3D much later on. So right now we're just talking about the distance between two values on a number line, or 2 points on a number line. So here's -2 and 5. And I just want to know basically how many spaces do I have to step to get from one number to the other. When we talk about distance, we don't care about direction. So let's write that down. Okay, I guess switching colors is good. We don't care about direction for distance. And different D word. Keep this in mind that when you're driving your car, you also don't care about direction, right? Your car doesn't notice that if you go north for 2 miles and then south for 2 miles, that doesn't equal 0 miles round trip, right? So when we talk about distance, we don't care about the direction that we're going. So the distance between -2 and 5, if you count up the number of steps, most likely you're going to come up with 7, unless you're super tired. But the distance between -2 and 5 is 7. And we can write this a couple different ways. I can say that the distance is 5 minus -2, right? That will give me 7. Or I can say this. It's the absolute value between 5 minus -2, which is also the same as the absolute value of -2 minus 5. And this is a nice one here, these two equivalent statements, because with the absolute value, all we're saying is that the order doesn't matter which one we plug in first. We just take the difference between the two numbers. We don't care about direction. The absolute value forces it to be positive. And in fact, absolute value really is distance. So the opposite of a number, so if I give you something like this, let me talk about this sign in a couple different ways. So this is this subtraction sign or negative sign or whatever you want to call that. Sometimes it means subtraction. And in the case of subtraction, we'll always have two numbers we're operating on. So something like this, 5 minus 3. And that is really a subtraction sign there because it's 5, take away 3. Another possibility is that that symbol is designating negativity. So we could have an example like -2, and in that case it's not subtraction, it's just indicating that 2 is negated. There's this other thing, one other way that we use this symbol, and unfortunately colloquially we say these things interchangeably, but in this case if I give you something like this, so technically this would only be read correctly as the opposite of -3. So you see this one turns out to be a negative, this is negative, and these two are both opposite. Now, do we say it like that every time? Not really. Sometimes we say the negative, negative, negative. Anyway, we can deal with that colloquially, but mathematically those are really opposite signs. So when we talk about the opposite of a number, let's say I give you 4. The opposite of 4 is -4, right here. But the opposite of -4 is 4. In other words, the opposite basically just means on a number line to take the mirror reflection across 0. So the opposite of 4 is -4. The opposite of -4 is 4. Okay, so now let's talk about the definition of absolute value of a number since we just brought that up with the distance. The absolute value is defined in this way. It's a piecewise function really, which just means it's defined in pieces. We do different things depending on what number is plugged in there. So the absolute value of A is A if A is greater than 0 or equal to 0. So in other words, if I plug in a value, let's do this. If I take the absolute value of 3, well, the absolute value, basically most students think of it as making it positive. That's fine. Or we can think of it as what's the distance that 3 is away from 0. Either one of those interpretations is good. The absolute value of 3 really just turns out to be 3 then. In other words, the absolute value in those cases means nothing because I can just drop it. What's inside was already positive, so the absolute value really is a non-operator. However, if I take the absolute value of -3, then quote-unquote making it positive, how else can I force that to happen? Well, the absolute value of -3 is the opposite of -3, which gives me +3. So you see, the absolute value of a negative number, that's what we're saying here. If the number that's inside the absolute value signs is already negative, then the absolute value signs basically just take the opposite of that number. Now notice that this sign here, not a negative sign. This is an opposite sign. So we're not saying that necessarily what's coming out of there is negative. We're saying that it's the opposite of what we had plugged in, which was negative to begin with. Okay, so let's do this example. The absolute value of negative 5 would be 5. But look at example B. This is saying the opposite. So again, this symbol is the opposite now, right? Since you can't see me point, I have to draw. Okay, so the opposite of absolute value of 5 is going to be negative 5. The absolute value of 5 is 5. The opposite of the absolute value of 5 would be the opposite of 5, or negative 5. And the final example for this section, find the opposite of each number and the absolute value of each number. So the opposite will be 32, right? The opposite of a negative gives me positive. The absolute value of negative 32 is, in fact, 32. So in this case, the opposite of negative 32 is the same as the absolute value of negative 32. The opposite of 17 will be negative 17. The absolute value of 17 gives me, yes, 17. Okay, so this is the quick introduction to the basics. And if this class already, this lecture is feeling really easy right now, then likely you're in the right place. If you're already overwhelmed, then that's not a really good indicator.